The Poisson's ratio is very important material property parameter because it gives us the key information about the material's deformation under different loading. My name is Jagadish Atole, and in this video we are going to discuss a very interesting material property parameter, that is Poisson's ratio. Do subscribe the channel and press the bell icon so that you never miss any new learning video from the Designgekz. Without any further delay, let's deep dive into the topic. In many industry, we use the pipes, cables, rods, different kinds of beams or bars which are made with the different materials, and all these materials needs to be tested for its strength by stretching it. Let's take an example of a bar having length L and stretch it along its length with the force P. You'll notice that the length of the bar increases, or we can say the elongation happens because of this stretching force or tensile force P. So the length increases from L to L plus delta L. But that's not the only change that will happen with the bar because of the applied force. Obviously, the length of the bar will increase, but the bar gets thinner. That is, the lateral dimensions will decrease from D to D minus delta D. That means the deformation is occurring in both the direction. To find this deformation, the scientist Simeon Denis Poisson coined a ratio which we now call the Poisson's ratio. More precisely, we can term this Poisson's ratio as when the material is loaded within the elastic limit, then the ratio of the lateral strain to the longitudinal strain remains constant. And we know the strain is the measure of deformation, and it is defined as change in dimensions divided by the original dimensions. And if we consider for the longitudinal strain, then it would be the change in length divided by original length, or we can consider as a delta L upon L. And for lateral strain, it would be the change in diameter divided by the original diameter, that is delta D upon D. So mathematically, the Poisson's ratio is lateral strain divided by longitudinal strain, and it is denoted by letter mu, or it can be denoted by 1 upon m also. So the Poisson's ratio will be delta D upon D, that is lateral strain, divided by longitudinal strain, that is delta L upon L. Basically, this longitudinal strain is the ratio of axial deformation to the original length, or it is also defined as the deformation per unit length in the direction of the applied load, that is representing as delta L upon L. And the lateral strain is the strain produced at the perpendicular to the direction of the applied force, and that is indicated as delta D upon D. Now the lateral strain in the formula is shown negative. So why the minus or negative? It's pretty simple. When you pulling the bar with the tensile force, its length increases from L to L plus delta L, means the longitudinal strain is positive. But because of this longitudinal increase, the lateral dimensions decreases from D to D minus delta D. That's why the lateral strain shown here is negative. And suppose if we do the reverse, means if you apply the compressive force, then the length will decrease from L to L minus delta L, and it becomes negative, and the lateral dimensions will increase from D to D plus delta D, means it is positive. So this is applicable for the isotropic materials. The isotropic materials are the materials which have the same properties in all the directions, and we are also assuming that the material is deforming within the elastic limit where the stress is directly proportional to the strain. The theoretical range of these possible values for the Poisson's ratio varies from -1 to 0.5. In actual, the most materials have the Poisson's ratio of somewhere between 0 to 0.5, and most metals have the Poisson's ratio of around 0.3. Now, the most materials which shows the Poisson's ratio values between 0 to 0.5. For them, when the material is stressed with the tensile force or the tensile force is applied, these material contracts in a lateral directions, means the lateral dimensions decreases, and the material which shows a nearly the zero value of Poisson's ratio will not get contract in a lateral directions, means there is no change in the lateral dimensions when the tensile force is applied in a longitudinal directions. The cork material which behaves this way, which has nearly the zero value of the Poisson's ratio, and this cork material is used in the wine or the champagne bottle because here we require the material which should not expand in the lateral direction while pressing it or inserting in the bottleneck. The material which have negative Poisson's value are called auxetic materials, and these materials expand in a lateral direction when stretched longitudinally, and it will contract laterally when compressed with the compressive force in a longitudinal directions. These are mostly the engineering materials or the foam materials. Here are some materials Poisson's ratio values. For rubber it is 0.49, for steel it is 0.27 to 0.30 depending on the grades of the steel. Then for brass it is 0.331, for bronze it is 0.34, for a concrete material which is a brittle one, that is 0.1 to 0.2, for glass it is 0.18 to 0.3, and for the cork material it is nearly 0. Let's take a numerical example for calculating the lateral strain from the Poisson's ratio. The question is, an steel bar with the length of 1 meter, that is 1000 mm, and radius 20 mm is stretched 2 mm. So calculate the radial contraction in the lateral direction. So from the given data, the steel bar is having the length L as 1 meter, that is 1000 mm, that is the L, and radius R is 20 mm, and it is stretched 2 mm, that is delta L is 2 mm in our case, and this is the length L, which is the 1000 mm, and delta L, that is 2 mm, and we are stretching it. So here is the Poisson's ratio for the steel is 0.30. We'll consider the upper limit. The longitudinal strain, that is change in length upon original length, that will be the delta L upon L. Lateral strain is the change in radius upon original radius, that will be the delta R upon R, as we are considering the radial dimensions. And we know the Poisson's ratio is lateral strain upon longitudinal strain, we'll get delta R upon R divided by delta L upon L. And if we rearrange it for the delta R, it will be the mu, that is Poisson's ratio, into R into delta L upon L. So if you put the values for this, we'll get the mu is zero point 0.3, R is 20, delta L is 2, and L is 1000. So we'll get delta R is equal to 0.012 mm, and this is the radial contraction in the lateral direction. So let's summarize the Poisson's ratio with some key points. The Poisson's ratio is very important parameter for determining how the material responds to the applied load. And the Poisson's ratio value ranges from -1 to 0.5. Generally, if the Poisson's ratio is in the range of 0 to 0.25, it indicates the brittle materials. And if it is between 0.25 to 0.5, it indicates the ductile material. And if the Poisson's ratio is 0.5, that is the change in volume is 0, it represents the non-dilatant materials. And increase in the Poisson's ratio indicates increased ductility. So this is about the Poisson's ratio. Stay tuned with the Design Geeks for such learning videos. Thank you.